Welcome to NASA Edge's exclusive coverage of Tower Rollback for Parker Solar Probe. We're going to cover a lot of ground in today's shows from a lot of different locations. Franklin is going to be on the roof of ULA's Atlas Spacecraft Operations Center with heliophysicist Eric Christian. And of course, Tiffany Nail and Mick Woltman are going to be out at the pad where, as you can see, Tower Rollback has not begun, but it will begin shortly. And of course, I'll be back in the studio here managing things from Hangar AE. And joining us now is our first guest, who appears like he's ready to actually go out and touch the sun.
I am ready, Blair. I've got SPF 10,000 on. I've got my darkest shades, and I'm going to the sun with Parker Solar Probe.
That's
what
awesome.
A mission.
Thanks so much, Jim, for coming on the show. Jim Green, friend of the show. Great to have you. You know, the last time we were on a show together, we were talking about Mars.
Yeah.
For Mars Insight. Well, now NASA's swinging its focus right around to the center of the solar system to talk about the sun. So my big question is, with Parker Solar Probe, what are some of the big questions we're trying to ask with regard to the science for Parker Solar Probe?
Well, we know the sun constantly outgasses in all directions, and that was actually not believed for many decades. It really was Eugene Parker that said in the late 50s that particles must be accelerated and blasted away from the sun. Scientists at that time thought, well, that can't be. The sun is so massive, and it would hang on to everything. So it's all about how do they get accelerated, because we know that's happening.
And so we kind of feel this effect in space weather and things here on the Earth. But how is this up-close look at the sun going to actually help us understand that better?
Well, I view Parker Solar Probe, because as you know, I'm a planetary scientist. I have analogies like ground truth. You know, for Curiosity roving Mars, it measures clays, it measures hematite on the ground. From the orbiters, we see what those spectra are, and then we know everything about Mars in those layers, because we can see the same spectra. Parker Solar Probe's doing the same thing. It's doing that ground truthing. We're going to be in an area that is so exciting, where solar wind, we believe, will be accelerated, where we'll see huge magnetic fields passing by us as coronal mass ejections make their way out into the solar system.
And it's kind of amazing because, I mean, typically, you know, we're not supposed to stare at the sun.
Yeah, right.
You know, and
don't do that.
And getting close is kind of a precarious thing, but we've got this heat shield, and we'll learn about that later. But really, what kind of data will we get that close? It almost seems like it's too powerful to get data.
Well, the first thing that's going to be happening as the spacecraft makes its way around the sun at what we call perihelion, that's closest approach, does that 3 times a year, is it will start imaging that area, and then it will fly through that area. Now, the instruments that are going to be on board are magnetometers to measure the magnetic field, particle instruments that will measure these high-energy particles that are being accelerated flying by the spacecraft. And so it has quite an array of fabulous instruments to be able to make those kind of measurements.
Jim, we've got to go, but I tell you, thanks so much for the information. And I look forward to talking to you about the data once it actually starts coming in, because it's going to be exciting.
It will be. My pleasure.
Thanks so much. Well, I tell you what, obviously we're going to get a ton of data from Parker Solar Probe, and Franklin had a chance to sit down with lead scientist Nicky to talk about the instruments on board that are going to get that data.
Now, you're going to be collecting a lot of science data with Parker Solar Probe. Tell us about the instruments you're going to use to collect that information.
So we have a wonderful payload that was very carefully thought about and put together to make sure that we could make all of the measurements that we really need to do to answer these groundbreaking science questions. So we have 4 instrument suites. We have a white light imager, which we call WHISPER, that is going to look around the side and take images of the solar wind that is about to impact the spacecraft. And so it's really going to help us kind of unlock all our other measurements. We have the fields suite that is going to measure all of the electric and the magnetic fields that we want to measure, and also any waves, any signatures that happen to be embedded in the solar wind. We have the ESA suite that measures the high energy particles. So these are the kind of nasty guys that are associated with shocks and with flares and coronal mass ejections. And then, certainly not least, we have our SWEEP suite that is measuring kind of the bulk solar wind. What is coming, what is hidden in the solar wind? What are all the different particle populations? what is the temperature, the velocity, the density. And so when we put all of those measurements together, we'll be able to answer our science questions.
Now, these suite of instruments, are they new, or are these off-the-shelf components that you use to build?
A lot of the instruments are very similar to ones that have flown before, but they are in very challenging environment. You know, for example, we have flown radio wave antennas on many missions, but not when they're going into 3 million degree material. We also have an instrument on the front of the spacecraft. I always refer to it as the bravest instrument because it takes no shielding, no protection from our amazing heat shield. It peeps out around the side. It's a simple instrument. It's a Faraday cup, which have flown on many NASA missions. But now we're asking it to work in this incredible environment. And so it is made with very exotic materials. And even though it's a simple instrument, boy, was that a challenging thing to get achieved.
Talk to me about the challenge of building that instrument to work in these extreme environments.
One of our biggest challenges is not even just the heat. So we're in 3 million degree plasma. Yes, that's awful and hot and dangerous. But our orbit is very much like the petals of a flower. So we go very close to the sun on one side, and then we come out around the orbit of Venus on the other, which means we go very hot and then very cold. Now, if you think of taking any material and heating it and cooling it many times, say 24, which is the number of orbits that we have, most of the time it will change its property. It will either become elastic or it'll become brittle, but it won't be the same 24 times later. All of our materials have to be the same. And so finding materials that would actually be able to withstand these changes was, of course, a challenge. And then testing them. The Parker Solar Probe spacecraft will be seeing just less than about 500 times the amount of sun we see here at Earth. So 500 suns in the sky is what Parker Solar Probe will be experiencing. And so how do you test it? We actually had to build test facilities just to be able to do this. We used reconditioned IMAX projectors because it turned out that the light that they put out is very much like sunlight. And so every single thing about this mission is challenging.
Well, can I go back to the IMAX projectors? Mm-hmm. What does that look like? How many projectors? What kind of facility do you construct this projector field to do this test?
So the original plan for this particular instrument was to use a solar furnace simulator in France. The problem there was that it only works during the day, and it only works if it's not cloudy. And so we couldn't get long runs to be able to get continuous hours and hours and hours worth of data. And so they actually constructed their own test facility. So up at the Smithsonian Astrophysics Observatory in Boston, they actually constructed basically a vacuum chamber, and then they took the 6 IMAX projectors and sort of chained them together, and so that would provide the right amount of illumination with the right amount of scattering angle for the light, the heat, and also firing particles at the same time to be able to really simulate what that instrument is going to see when we get very close to the sun.
Is there an opportunity for Parker Solar Probe to collect any science on its way to Venus and back to the sun?
So our intention is to have the instruments on it as much as possible. So we will have them on for the full journey in around the sun and the full journey out. The only time that we will not have the instruments on really is if we're doing a major maneuver on the spacecraft, or if we're sending our data down when we need all the power to go into the system that is going to transmit the data. And so we switch off the instruments during those periods. I often get asked, are you going to do science around Venus? And unfortunately, my quick answer is always no, because whenever we are flying past Venus, that is our prime time to get our coronal science data down. And so the instruments are planned to be off when we do our Venus flybys. There is one later in the mission. We actually do 7 of them. There is one when the instruments can be on, and we are excited about what kind of science we'll be able to do then. But that's a number of years away, and few days away from launch. Everybody's focusing on the launch right now.
Where are you going to be for launch?
For the launch itself, I will be honestly as close as physically possible to the Delta IV Heavy, but in reality, I will be somewhere around the press building, probably looking through my fingers at the site of the Delta IV Heavy. But actually, if they let me light it, I would.
I'm sure you would. I'm here with Dr. Eric Christian, who is a Heliophysicist from the Goddard Space Flight Center. Now, Eric, I've talked to you many times about the sun, and every time I do, it seems like your title is changing. So what is your job with the Parker Solar Probe?
So I have different roles on different missions. For Parker Solar Probe, I'm Deputy Principal Investigator of the ESIS Instrument Suite. ESIS stands for Integrated Scientific Investigations of the Sun.
Now, what are these instruments going to look at?
So ESIS has two instruments which look at solar energetic particles, the highest energy particles coming from the sun. These are particles that are moving up to more than half the speed of light.
Now, why is it important to learn about these particles, and what will it tell us about the sun?
So solar energetic particles are important because they're the damaging part of space weather. They can damage spacecraft in orbit, and they can even hurt astronauts, especially if they get away from the protective shield of the Earth's magnetic field, which it protects the space station. But if we're going to return to the moon or go to Mars, then the astronauts are going to want to know when solar energetic particles are coming.
We, before the broadcast, talked about the type of predictions you want to do with space weather, and you compared it to hurricanes. Tell me a little bit about it.
So terrestrial weather uses models of the atmosphere to predict where hurricanes are going to hit, how strong they're going to get, how weak, when they weaken. We want to get to the point where we can predict space weather in the same way. So we know where solar energetic particles are going, where coronal mass ejections are going, and how strong they're going to be. And in order to get to the level where we can make models that predict that, we need to understand a couple basic science questions, and that's what Parker Solar Probe is going to do for us.
Now, the space weather that comes from the sun goes far past the Earth. You say as far as Pluto sometimes. Tell me a little bit about what you talked to me earlier about the Mars and the atmosphere and what is thought to have happened.
So one of the theories for why Mars lost all of its water and atmosphere is that when it solidified, it basically lost its large magnetic field, the way the Earth has a magnetic field. And that allowed the solar wind to, over 100 million years, blast the atmosphere and the water off of Mars, and that's why Mars is a desert now.
And that's definitely the type of things that we do not want to happen here at Earth.
That's right. But we have a strong magnetic field on Earth, and as long as the core stays liquid, which is going to be long past when you and I are here, we're going to have a magnetic field.
Talk to me a little bit about the other science that's going to take place outside of the particles that your instrument's going to look at.
So the other two questions, other than the solar energetic particles, are why is the corona, the atmosphere of the sun, hotter than the surface of the sun? Normally when you get further from a fire, you get colder. This is weird. The atmosphere is millions of degrees, whereas the surface is only about 6,000 degrees Kelvin. Understanding that really will help us understand how the expansion and how the solar wind goes out. So the solar wind is also accelerated out to 1 million miles an hour in close to the sun. That's the other question that Parker Solar Probe is going to get close enough to be where the action is happening for the first time.
Now it's going to get so close, but it's not going to get burned because of the heat shield that's on the outside of the Parker Solar Probe. Is that right?
That's right. Except for a couple small parts, everything else hides in the shadow behind this heat shield, what we call the thermal protection system. And that keeps us, my instruments, at room temperature.
Thank you, Eric. Speaking of thermal heat shield, Blair had an opportunity to talk to Betsy Congdon, who is the engineer who is working with the heat shield on Parker Solar Probe. Here's that interview.
Betsy, we're really excited because Parker Solar Probe is going to get all new science we haven't seen. But that also means you had to design an entirely new thermal protection system. Tell me about this new system.
So the thermal protection system team has been working for 10 years and really 60 years in the life of Solar Probe in some form or another to figure out how to do a heat shield that will make this mission possible. It's basically a lot like a honeycomb panel you might find actually on the spacecraft itself or in an airplane. You have two face sheets. They're made of a carbon composite that's a lot like the graphite epoxy you might find in your golf clubs. It's just been superheated so that it can survive at the temperatures. And then inside there's a carbon foam core that actually takes a lot of the heat, and it's 97% air, so it's basically a foam.
Now, how do you manage the different extremes in space? Because obviously when you go close by the sun, it's at its hottest, but sometimes you're far away and you still need protection. How does that work?
So the heat shield is going to be at its hottest, at its closest pass, about 2,500 degrees Fahrenheit. And then, yes, it does get cold. It gets, down to room temperature, a little below at different points in the mission. So we've tested it through that whole range of extremes and actually beyond those extremes to prove out that the system will work exactly as intended during the mission.
Speaking of which, how do you actually test the temperatures? Because, I mean, every time I go out on the beach and basically burst into flames. So I'm wondering, how do you test this kind of shield at those temperatures?
Yeah, there are actually facilities all over the country and all over the world that can simulate temperatures like this. It's just a little tricky, particularly because we need to actually also simulate the vacuum of space at the same time. And that's where it really gets tricky, is not just the temperature side. There are heaters, there are facilities that look at actually the solar spectrum and putting the right amount of light on it. There are all sorts of facilities, and we've used many of them all across the country, prove out all of the different components to make this mission a reality.
And that's cool, too, because you went beyond your expected parameters, as most NASA missions do, just to make sure you're safe.
Of course, yes. So not only do you test to the temperature you think you're going to get to, you test beyond that a couple of hundreds of degrees. Usually we talk about a couple of tens of degrees, but in this mission, we really had to go hundreds of degrees.
It's basically cooking.
Yeah, definitely.
Space cooking. During the mission, as you make these passes of the sun, you actually have to orient the spacecraft to keep the instruments safe. How did you design a heat shield to do just that?
So the heat shield is one component that actually makes this possible. As we go around the sun, the heat shield always has to stay between the spacecraft and the sun so that everything stays in the shadow or the umbra and make sure that it is working properly. So not only do we have the heat shield, which is basically oriented, aligned, in a very tight number to be exactly where it is, we also have autonomy software that's actually moving the spacecraft around in the right orientation. We don't joystick it around the sun, it's doing that all autonomously, which is actually one of the amazing parts of this mission.
And I would imagine that heat extremes can actually cause material to move and fluctuate. How do you handle, make sure it doesn't become like a big pancake, or it doesn't change shape altogether?
So we, like throughout all of this testing, we really had to understand how this system was going to work as it gets close to the sun. And what actually happens is, as you can imagine, so the top face sheet is at about 2,500 degrees Fahrenheit. The bottom face sheet of this shield is at about 600 degrees Fahrenheit, and it's all connected. So what actually happens is the top wants to grow more than the bottom. And what happens is the heat shield actually smiles, basically, we like to say, at the sun. It gets a little bit bigger, which helps protect everything behind it.
Now, that's a nice peacekeeping move, too. You don't want to frown at the sun.
You don't want to anger the sun,
You're
exactly.
that close. You don't want to make it angry. Now, it's a long mission. Obviously, your work on the heat shield will be done at launch. So what are you going to do over the next 7 years as this data comes in? I mean, every time data comes in, you'll know that you and your team have been successful.
It has been such a privilege to be part of this team over the last 10 years, and I'm really excited for the next 7. We will be rewriting science textbooks, and that's just amazing. When the data comes down in its raw form, I probably won't understand what it is, but I will be really excited to see the papers and the excitement from the scientists as it comes in, and I am so excited to be part, just, a small part of just making that possible and making the scientists' dreams come true.
Well, tower rollback has not actually begun here at Space Launch Complex 37. However, we're going to go ahead and go to our friends out at the pad, and they may actually tell you when roll begins. Tiffany?
Blair, we are here for tower rollback at Complex 37. Mick, this is a historic mission. This is also NASA's second use of the Delta IV Heavy, but LSP's first. Let's talk about when LSP matched the Delta IV Heavy to Parker Solar Probe.
Yeah, you're correct, Tiffany. This is our first Delta IV Heavy for Launch Services program. Because of the energy required to get Parker Solar Probe on its way to the sun, Launch Services program looked at all the vehicles, and we chose the Delta IV Heavy back in 2015 due to some of its unique features. First and foremost, the Delta IV Heavy has 3 hydrogen-fueled first-stage common booster cores, all 3 powered by an RS-68A engine, which provides enough thrust and power to get out of Earth's atmosphere with the vehicle. Then sitting on top of that, we have a Delta Cryogenic second stage, which is powered by an RL-10B, which provides just enough power to get into the initial escape trajectory for Parker Solar Probe. And of course, we want to make sure Parker's protected on its way up through ascent, so we have a 63-foot, 5-meter fairing that is over Parker Solar Probe, protecting it during its ascent through the Earth's atmosphere.
Now, ULA, for the rollback, walk us through what happens with the rollback in the tower.
So the teams are together, they've done their pre-test briefing and gone over all the procedures, make sure everybody understands what needs to be done to get the tower rolled back around from the vehicle to its parked position. So what they're doing is moving all the decks out of the way, moving all the doors, making sure nothing is touching the vehicle so that they can slowly move the tower out and expose the Delta IV Heavy to the sun here and show us its beauty.
Now let's talk about when the spacecraft arrives at the launch pad and it gets hoisted up. This is very unique. So let's talk about Complex 37, the uniqueness of this pad, and also how they hoist that spacecraft up on top of the Delta IV Heavy.
Yeah, Complex 37 has a long history here at Cape Canaveral. Started back in the 60s. It was built in 1959 for the Apollo program. They actually launched Saturn 1s and Saturn 1Bs from Complex 37. And in 1972, they deactivated the pad after that. ULA came along in 2001. And reactivated the pad and made some modifications to it, which was really neat. A couple of them that they made is the Delta IV Heavy, as you see, 3 first stage common booster cores. So they bring those out from the horizontal integration facility, and they have a big hydraulic arm that pushes and just lifts that up into the tower. That is a unique feature at this pad. But as you mentioned, spacecraft encapsulation and hoisting, that's another unique feature here of the mobile service tower. They actually have a chute, it looks like. It's like a tunnel on the back of the tower that when they bring the spacecraft out encapsulated, they lift it up through that chute and into the tower, into the clean room, and then mate that to the Delta IV Heavy, which keeps everything clean for them. Parker Solar Probe also has a solid fueled Star 48 BV motor, which was provided by Northrop Grumman Innovation Systems, and that is what we call the third stage, and it will provide enough thrust for Parker at the end of the mission to get it on its trajectory headed towards the sun. So we're very happy that ULA partnered with Northrop Grumman Innovation Systems and LSP, and we're looking forward to this launch with this 3-stage vehicle.
Now when launch happens, it looks like the Delta IV Heavy is engulfed in flames. Explain to our audience what is really happening.
Yeah, it doesn't actually catch on fire as it looks like. What's happening is, as I said, the 3 booster cores are hydrogen fueled. So they start purging the hydrogen through the RS-68A engine, and that kind of bubbles up around, and when the engines ignite, it ignites everything around it, and it just kind of looks interesting when it happens.
So for LSP, we have 2 more missions this year, ISAT-2 and ICON. And then this is our 4th mission. We have a total of 6 for 2018. Mick Woltman is going to be part of the KSE broadcast. He's going to be our rocket scientist. So LSP family is cheering him on and wishing him the best of luck. I know you're going to hit it out of the ballpark.
Tiffany, you know I love talking about rockets, and I'll talk about them any time of the day, including this morning for Parker Solar Probe. Thank you very much.
5, 4, 3, 2, 1, 0. Liftoff of the mighty Delta IV Heavy rocket with NASA's Parker Solar Probe, a daring mission to shed light on the mysteries of our closest star, the Sun.
You know, Franklin, we may have missed the rollback during the broadcast, but when it comes to the launch, the Delta IV Heavy didn't disappoint.
Not at all. And, this was my first Delta IV Heavy launch, and Parker Solar Probe is on its way to the sun.
You're watching NASA Edge.
An inside and outside look at all things NASA.